Hi folks, now we're going to talk about the planetary system. This is the next chapter in Kaufman's and Cummings, and I'm going to discuss it in terms of a few items. One is the planetary system, just to give you an idea of the generalities of the solar system, and then we'll talk about solar system formation, and then we will talk about exoplanets. It turns out that some books talk about exoplanets in this frame of reference of solar system formation, and others talk about it in other frames of reference. This is one that's preferable to me in that the solar system, and we're finding whenever we look at other star systems that they have planets as well. And we'll talk about that a little bit later. So that's sort of where my heart lies as far as how this thing is organized. But let's take a look at this picture. This picture is from the Astronomy Picture of the Day. And as you know, if you want to discuss, discuss one of these things, it's an extra credit opportunity. So please take a look at the extra credit opportunities in the syllabus section of our eTudes website or whatever learning management system we've got, and then avail yourself of finding something about your birthday that's significant to NASA as far as astronomy is concerned. Anyway, this particular picture or set of pictures was taken by, I believe, the Pioneer spacecraft, and you can take a look at that in this particular picture of the day. What is interesting, though, is they took the camera and focused it back on the planets and the sun. So the sun is way over in here, and it has been pushed down in intensity, otherwise we'd be able to see anything. And then, in fact, what has happened is they've blown up particular regions in space, and then what we can see here, here's an N, this is where Neptune is, and then here's the picture of Neptune. Similarly, here's Uranus, and there's Uranus, Saturn and Saturn, Venus, and Venus is that little dot right there, and here's the sun. Here's Earth, and there's Earth here, Jupiter and Jupiter, things like that. So it is a very interesting picture, sort of, if you will, a photo album of us. As you know, the solar system is made up of planets and the sun, and there are some other little guys involved. We have now since had this new categorization called dwarf planets. New is probably not a really good statement, but some of you probably asked what happened to Pluto. Why isn't it no longer a planet? Where did it go? Well, Pluto is still there, but has now been categorized as something else. Okay, it is no longer considered a planet because planets have 3 requirements, and we'll talk about that in a little bit. Basically having to do with size, if it's part of a swarm, and naturally has to go around the sun. Okay, so Pluto is about as big as this guy over here, which is one of the asteroids in the asteroid belt. Okay, so one of the things I want to get across in this particular section is the similarity between the planets and categorize them in terms of what they look like and things like that. Okay, so we can categorize these groups into a variety of different pieces. And remember what we're after here. We're trying to understand the solar system because we want to understand how it was made. Okay, and part of what we do is categorize things. Left versus right, black versus white. Yeah, I said left versus right and black versus right. That's weird. Okay, anyway, tall versus short, heavy versus thin, just everything under the sun you can categorize. And so what we want to do with the solar system is be able to describe it, and so we use these ways to this categorization to define things. And then we look for patterns. And as you may have heard before, we humans are really good at finding patterns in anything, even patterns that aren't there. So here we're going to try to figure out a pattern, and then we're going to see how these patterns were created and how these patterns evolved in time. Now, this is pretty interesting. I mean, Genesis does this in the first few pages, and if you read Genesis carefully, there are a couple of different ways that the world or the universe was created. Okay, here I'm going to give you just one, and we're just going to talk about, this is from evidence, trying to link up these patterns. Okay, so one of the things that we need to consider, though, is how do we determine what these patterns are? How do we characterize these things? So in reality, what we're doing is we're measuring distances, we're measuring masses. So for example, distances to planets, sizes of planets, the mass of planets, their density, how are they, what are they made out of? What is their internal structure, and how do they move? Now, the movement of the planets is going to be one of the key parameters in order for us to come up with our creation story for the solar system. Okay, so we're going to take a look-see, take a look around the solar system and take a look at what we have seen and what it looks like now. So here is the moon from a picture of the far side, care of the Soviet Union and one of their satellites. And you can see the date for yourself. And then we were there, okay, footprint. And there are satellites that are traveling around the moon right now and can actually picked up evidence, in tire tracks and things like that of the Apollo probes and spacecraft and landings. If you look at Mars, this is what it looks like through a pretty good telescope. Mars is actually up and visible right now. Right now means late September 2016. And periodically it gets into view and disappears from view because it gets too close to the sun. Be that as it may, we have sent landers to Mars. This is not a picture of the lander. This is of the first flyby of Mars, and it looks very different than what we had anticipated before then, because you probably have heard, various Martian invasions of the Earth through the century, and that continues to be a source of fun for science fiction. But what you do see is, since 1965, is this place is pretty stark. We've got lots and lots of craters. And then when you go to it, this is look at that clarity of that picture. But if I showed you this picture and did not indicate it that it was from Mars as implied up here, and that it was a rover, then I could easily say that this was a picture at the not Obeyoyo, but the crater, the Amboy crater out by Barstow. And this is igneous rock, and there's a bunch of sand there and stuff like that, and you'd be hard placed to come up with a characterization that was any different. This is what Saturn looks like as of 1970, because we hadn't gone there yet. Naturally, our data improves when we go there, either with our tools or us ourselves. But one of the amazing things is to view Saturn from a telescope. Telescopes, as you saw from the last section, are very, very simple objects. A couple of lenses or a mirror and a couple of lenses. I mean, something not much more complicated than a pair of eyeglasses. And you can see something as totally amazing as this. I mean, the first time anybody looks at Saturn and sees the rings for the first time, it's just like their mouth drops. It's just totally amazing. It's unbelievable. Yes, indeed, it has rings. I mean, it's crazy. It's out of this world. And then when we go there, we get even clearer pictures. This is from the Cassini spacecraft from about 10 years ago. And as you know, one of the spacecraft, we're going to lose one of the spacecraft pretty soon. It's going to go crashing into, I think Cassini is still on its last legs. Okay, well, you guys can look that up. We can find out a little bit later. Now, Saturn has an interesting satellite going around it. We'll talk more about that in the section on Saturn and the other Jovian planets. But Titan has the possibility of life. Life there is not going to be like life here. These rocks that you see are basically water. Okay, I mean, it isn't liquid water, because water doesn't exist on Titan, but it is essentially, ice in various forms there. I mean, it's in one form, it's crystalline, but it shows up as dirt, if you will, there. Now, the thing that takes the place of water on Earth, there on Titan, is alcohol. Methane and ethanol and things like that, and methyl alcohol and ethyl alcohol, they come down and as rain and form these big lakes. And so alcohol takes the characteristics of water on our planet there on Titan, in that alcohol has 3 phases there: liquid, solid, and gas. So you can have, it could be raining alcohol. Now, I don't suggest you go there just so you can get a really good margarita just by sticking your tongue out and gulping it in. That won't work. But the idea is that we seem to think that life requires a medium for transportation of food and waste, and that's what water does on our planet, for us, right? And so there we could have an alcohol-based life form that would be utilizing a hydrogen economy, if you will, rather than an oxygen economy, which we use. Okay, so here is what Jupiter looks like at about that same time frame, 1970. Notice that, it's not a very clear picture. And then, boom, from Cassini again, 60-kilometer resolution. I mean, you can see some very, very fine detail here. Venus from 1970, again, we weren't there. But then a few years later, the Soviets landed a spacecraft on Venus, and it didn't last very long, but it did land. We have since gone back with a variety of different mappers, and this is a radar image. Look at that clarity there. A radar image from Magellan from 1992, 100-kilometer resolution. And you can see the ocean basins and the continents as you would on our planet. Naturally, there's no water on Venus, so you really don't have oceans and things like that. It's just way too hot. But you do have these highlands and you do have these lowlands there. Now we're going to get to Uranus. This is a picture of Uranus from the Hubble Space Telescope. And Uranus is kind of an oddball of the solar system in that it spins on its back, as the BBC program of the planets would describe it. But its rotational axis is right here, along here, and this is the same plane. I mean, the rotational axis is right on the plane of it going around the sun. So the sun is over here, say, and the planet goes around it like so. Okay? And this here shows a picture of 50 years of exploration, and one could take a look at the different NASA missions just by going to, as it says here, www.nasa.gov/missions, and you can take a look at all these missions that are currently going on. And the websites are still maintained even when the spacecraft is done. Okay, so they don't remove it. Okay. So the picture here shows us, we sent a few spacecraft over to take a look at the sun. We have here only a couple going out to Mercury, and we have a lot going around, the moon here that's the moon. So it's got all the Apollo spacecraft and stuff like that. And here, this is Venus, and it doesn't show all the ones going to the Earth. And then we've got the ones going to Mars. That's a favorite because we want to make sure there are no Martians that are going to attack the Earth. We have some that have gone to the asteroids. And here's the ones for Jupiter, Saturn, Uranus, and Neptune. And we have those two spacecraft that have left the solar system, the Pioneer spacecraft and the Voyagers. Okay, so now we get back to our question, what is the solar system? So I think you could probably do this on your own, but there's no sense, really. The solar system is defined of planets. Some have moons and rings. Then we have the asteroids, the comets, and the sun, naturally. So that really sort of defines it. Now you could include the dwarf planets, but that you could also argue is also included in asteroids and in comets. And here's the picture we've seen before. So one of the things we're going to point out now is take a look at some of the characteristics of these as a group. Okay, so, and we're going to break the group into subgroups. So looking at this subgroup and then looking at these two, maybe include these other two out here, and then we'll talk about these as well. So remember, we're trying to understand the solar system, its characteristics, so that we can figure out a way of how, what are these patterns and how would these patterns be created, and see if that makes any sense. Okay, so we talked about planet motions in the sky. Remember, retrograde and prograde motion, that's going to be key to our understanding what's going on. And what we find out, first of all, is all the planets are in the same plane. Okay, they do have this loop-to-loop behavior, and you can see that in stellarium, but basically they all are in the same plane, right? They all are very close to running around the plane defined by the ecliptic of the sun. Okay, so if you do go into stellarium, turn on the ecliptic and watch how the planets move. They never get very far from the ecliptic. All right. Now, as before, we indicated that we wanted to take a look at the physical properties of the planets, and here are some of the physical properties we're interested in. So the relative distances between these planets we discussed earlier, and it comes straight out of Copernicus, or if you will, comes actually from Democritus, a Greek astronomer. Okay, so basically as soon as you have a heliocentric universe that you're going to work from, or a heliocentric solar system, if you measure everything in terms of a relative distance between the Earth and the Sun, then you could find out what is the distance between the Sun and this little guy because of how it moves in the sky. This angle theta here is one that you can measure. For example, use the pinky rule. Find out how far of an angular separation there is between the Sun and this planet when the planet is furthest away from the Sun. When the planet is furthest away from the Sun, then what we'll notice, or what we'll see, I think it's obvious though, is that this angle here is 90 degrees. If I know this distance, and I know this angle, and I know this is 90 degrees, then I know this distance as well. Okay, it's proportional to that guy and this angle, right? The tangent of theta is equal to little d over big D. Now we can do the same sort of thing for the superior planets, those planets that have orbits bigger than the orbit of the Earth. And basically it takes a little bit more detail, a little bit more playing around, but basically it's the same sort of thing. You can determine little d in terms of the astronomical unit, or the average distance between the Earth and the Sun. And then we can also, given that, we can come up with these following values. We saw this a couple weeks ago, and the comment made there is that there isn't much difference between these numbers, between the numbers that Copernicus published and the accepted numbers now. Okay. Now, the only thing I want to point out to you is this is, Copernicus and these numbers here are relative to astronomical units. The basic difference is we know what an astronomical unit is. Astronomical unit is this number right here. We know the astronomical unit to within 3 meters, 10 feet. And look at all these things. This is roughly, it's naturally easier to say, 150 million kilometers. Okay, so we can do that by pointing a radar dish at Venus and throwing some signals at it and waiting for it to bounce back. There is a little simulation that the lab classes do that have come from Gettysburg College, and that simulation basically sends out a signal out to Mercury, which you can also do, and it waits for the bounce back. It would be nice to be able to have a detector like that on one of our telescopes and send it out and wait 10 minutes later for a signal to return. Anyway, so that allows us to measure the distance to those planets and figure out what the astronomical unit is. Well, now the example I want to, figuring out the planet mass is a little bit different. We talked about Kepler's third law, and we talked about Newton's variation of Kepler's third law, which is this equation here. Now remember, equations are used to keep score. It allows us to categorize things. And so what we're categorizing here is the mass of, say, Jupiter. And as we watch Jupiter, just as Galileo did, we'll notice the moons going around Jupiter. And what we can do is wait until the moon is over here, and then we'll just watch it as it goes around Jupiter until it returns to that spot. Okay? Using Kepler's law, we know how far away Jupiter is from the Sun. And by knowing the angle between Jupiter and the Sun, we know how far Jupiter is away from us, from the Earth. Okay, so I know little d. Okay, now I also know how big D is, because big D is being looked at through a telescope, and I know how big the field of view is of the telescope. As an example, last week we talked about fields of view in telescopes, and if I point the telescope to some object on the ground, then I know that the distance across, I can measure the distance across the field of view, say pointed at a stop sign. I know how big the stop sign is, and thereby how many stop signs fill up what I can see in the telescope viewfinder, and I can measure with a tape measure how far away that stop sign is. So the distance across the field of view divided by that distance tells me the angular size that I can see in the telescope. Well, I know by looking at the picture of Jupiter, I can then figure out how many Jupiters fit across the screen in my telescope. That allows me to figure out what big D is. Okay, so big D is something I measure in the telescope. Little d I get from Kepler's third law. Big G is a known quantity. 4 and pi are numbers. Okay, big G is gravitational constant. And the only thing left to do for me is to measure how long it takes to go for this moon to start here, to go all the way around its orbit, and to return. When I do that, that tells me what P is. So given all of this stuff here, I can figure out what the mass of Jupiter is. And that is true for any object I see out there that has something smaller traveling around it. I can figure out its mass. Pretty powerful tool. So now I know the masses of the planets. If I take a look at the masses of the planets, and I put them in terms of how many Earths does this thing equivalence to, then I find out that Jupiter is by far and away the heaviest thing out there, except for the Sun naturally, and it's about 300 times the mass of the Sun. Saturn, on the other hand, is about 100. Uranus and Neptune are about 15 times that of the mass of the Earth, not the size, the mass. And then these guys over here are little in comparison to it. So big difference between these guys up front, closer to the Sun, and these guys further behind. All right, now I already described to you how I can figure out the planetary diameter from the previous chart. It's basically the same thing. I know how big, what angle this subtends in my field of view, and so the angle that it subtends multiplied by, little d here, which I get from Kepler, and then a couple other constants thrown in, tells me what big D is. So I know how big the planet diameter is. If I take a look at the planet diameters, this is what it looks like. So again, Jupiter and Saturn are real big. Uranus and Neptune are smaller. And then the guys up front closest to the Sun are even smaller yet. So it really is these guys against these guys. Notice also that Jupiter and Saturn are almost the same size. Okay, they're not too far off. And by taking the planetary mass divided by the planetary volume, I can find out what their densities are. And you'll notice also a big difference between those guys up front and the guys further out. Okay, and the difference here is quite remarkable, right? These guys are very dense. Now, nobody is saying a planet is smart or dim, but they're more dense up here, and they're more fluffy out here. Okay, they're big and fluffy out here, small and dense here. Notice also that Saturn, if you could find a lake big enough, would float. And Jupiter and Uranus could float on some of the salty seas that are on the planet Earth. So, for example, Mono Lake and the Dead Sea may have those guys float. One has to take a look at what the densities I think the densities of the Dead Sea and of Mono Lake are about 1.3. So these two guys would these Jupiter and Uranus may float on both of them. All right, now this picture is to indicate that there is basically a lot of space in space. We have these planets and the other small guy objects, but it's mostly empty space. And if you look at a CD, the stuff is mostly along where the massive portion of the CD is, and that gives a good description of the solar system. Most of the stuff is in the plane of the orbits. Okay, now another way to the next thing to classify the planets is to look at the temperature, and we're going to then, so that's the next step in this. Okay, so that's it for this particular talk. Again, what did we get out of it? Well, I wanted to show you all the pictures we have of the planets and to characterize some of the elements associated with these planets so that we can next apply that to our creation story. Okay, so that's the thing that comes up next. Now, one of the things that would also be useful to do would be to take a look at the Planets series from the BBC. Okay, thank you.